All right. Well, I guess it wouldn't be technology if there wasn't some excitement through such a long day. It's been a fun and certainly very information-filled day. Sorry for the hiccup. The platform we're using appears to have had an issue, and we kind of got cut off a little bit. So we are set up and ready to go again. And this really is a perfect follow-on from the previous talk around observability and open telemetry. And so Ramon is the VP of our observability team here at Timescale, working on and managing the Prometheus project, the PromScale project, which originally based on Prometheus. And so, just go ahead and lead in. You can tell us a little bit about yourself and what you're going to do today, Ramon.
Sure. Yeah. So my name is Ramon Guiu. I'm based out of beautiful Barcelona. And I, as Ryan said, I'm a VP of product of observability products at Timescale. And I come from New Relic. So I joined Timescale 8 months ago. I come from New Relic. I spent 4.5 years there managing different teams on doing infrastructure. New Relic is a well-known vendor of observability and monitoring solutions.
Right.
And today I'm going to talk about what you can do with trace data. So Scott in the previous talk shared a little bit about observability, how trace data is important. So I'm going to show how you can use trace data in SQL to do some wonderful things and get amazing insights from, to better understand the behaviors of your systems.
Very good. All right, share your screen.
I'll go ahead now.
I love every time that anytime we talk about it, we say trace and observability plus SQL. Like, it's just not what most people expect. And I love that we can add that SQL part on. So this is exciting.
That's great. Yeah.
All right. I'll join you afterwards. You go ahead and have a good time, and we'll come back for some questions.
Sounds good. All right. Okay. So yeah, I mean, as more and more engineers adopt microservice architectures and cloud native technologies, understanding the behavior and failure patterns of our systems is key to ensure they are performing and delivering a great customer experience. Okay. So the problem with that is that it's really hard because those environments are made of many components and they are highly dynamic with auto-scaling and frequent deployments of new versions of our applications. And this is why observability is needed. If you think about it, observability is fundamentally an analytics problem. You collect a lot of data without metrics, logs, traces, events, maybe other things, like profiling data. And the thing is, you need to analyze it often in real time so that when a problem occurs in production, you can quickly query and analyze your data in any way you need to get answers to the specific questions that are relevant for that incident. So in this session, I will use a simple microservices demo environment that we've built to show you some of the invaluable insights that you can get about your systems by being able to query and analyze your traces using SQL. And for that, we will use 3 open source projects: Open Telemetry, which again, Scott has talked about in the previous talk; Grafana, who everybody knows about; and PromScale, which is a tool a product we're developing at Timescale. This is the agenda. Because Open Telemetry was already covered in the previous session, and Grafana, I guess pretty much everybody knows about it. I will just give a short introduction about PromScale, and then I'll jump straight into showing what the demo environment looks like and the actual querying using Grafana to trace data. By the way, the demo environment that we're going to be using is available on GitHub. You have the URL there. You can go and download it and use it. And we've also written a detailed blog post that covers everything about that demo environment: how to set it up, how to instrument your code with Open Telemetry, how to query the data, and build Grafana dashboards. I'm going to be covering especially the querying part of that is covered in the blog post. And in the blog post, you'll even go into more detail than where I'll go today. So I'll encourage you to check it out if you're going to dig deeper into querying data, Open Telemetry, and querying data traces using SQL. Okay, so the demo makes heavy use of PromScale and its capabilities. But what is PromScale? PromScale is an open source observability backend for metrics and traces. Okay, so it's one single backend for both, and it's powered by SQL. And it's powered by SQL because it's built on top of proven rock-solid foundation of Timescale DB, which obviously, as you know, is a time series database built on top of PostgreSQL. And therefore, as a result, it lets you query the data using full SQL. It also gives you a lot of other benefits like reliability, high reliability. You can create replicas. You can benefit, you can even store if you want, other types of data inside the same database. So it gives you a lot of, obviously having a, PostgreSQL as a backend to it gives you a lot of advantages. And in the demo, we will use SQL extensively to derive insights. On top of OpenTelemetry, PromScale also integrates with Prometheus for long-term metric storage and analysis. And it includes support for PromQL as well, the Prometheus query language. This is just the high-level architecture of PromScale. You can see that PromScale, uses Timescale DB to store the data. You can natively ingest Prometheus metrics and OpenTelemetry traces. And you can use Grafana, 𝗂𝗵𝗽𝗱, or any tool really that speaks SQL to query and visualize your data. Okay, so now let's take a look at the architecture of the demo environment that we will use. As I said, the demo environment is available on GitHub. If you want to deploy it yourself, it's very easy. You can just basically copy and paste the 3 commands in this slide in a terminal. And the only thing is that the only requirement is that you must have Docker and Docker Compose installed in your system. And Git as well to do Git clone. And with that, you'll be able to get up and running in a few minutes. You'll have to wait a few minutes and you will get the demo environment up and running. Already, with everything already set up and connected for you to start exploring your traces. This is the high-level architecture of our demo system. It's a password generator that has been over-designed as a microservices application. Okay, it doesn't make a lot of sense for a password generator like this, that is the only thing it's doing, you make a request and it gives you a random password, to be built as a microservices application, but is a simple example that people understand, and so it's easy to relate to it and understand how it works. Then the microservices application has been connected to an OpenTelemetry observability backend. Okay, it has a load generator that makes requests to the generator service. And then the generator service calls the upper, lower digit, and the special services to get random uppercase, lowercase digits, and also special characters to build a password. The lowest service is written in Ruby, and the rest are written in Python. All services have been instrumented with OpenTelemetry traces, and they send those traces to PromScale via an OpenTelemetry component called the collector that, we will not get in detail, what it is, but I encourage you to check it out. It's a very cool connector to help you collect telemetry from different systems and then process it and send it to a bunch of different backends. And the demo environment also includes Grafana. Already, again, everything is already connected and set up, and Grafana has been set up with a number of dashboards that we will use in this session to visualize the data. Okay, so now let's jump into the demo. I'm gonna open Grafana here. One sec. Hop. Okay. And so we have a number of dashboards that we've created and have been pre-created for this demo. We start with a very simple example. Okay, we want to say, look, using traces, we want to get what are the requests per second that are made to our application. And by the way, because our application, the only entry point is the generator service, we're going to be basically querying just all the requests that go through the throughput of requests through the generator service. So how do we do this? Let me show you what's behind. We're using a standard Grafana time series panel. And this is the query, a fairly simple query, okay? So we're creating time buckets of 1 second, and we're counting the number of rows in this bucket. And this is the table, is actually a view that we're querying. It's a span view. And this is a view that is exposed by PromScale to make you, so basically you send telemetry, that you send traces to PromScale, and PromScale automatically has built a schema for storing them that is optimized for performance and high cardinality and scalability. And there are a bunch of tables that are involved, but it exposes a view, this span view, to make it easy for users to query. And the other thing that we do, the only condition that we apply to it is that parent span ID is null. What this means is that spans, if you follow the previous session with Scott, a trace is a sequence of a span, a hierarchy of spans. The first span in the trace typically captures the entire the time it took, to run the entire trace, okay? Because all the other spans are in it. So if you think about it, the first span in that trace is called the root span. It doesn't have any parent, and so you can use that to understand how many requests to that endpoint, how many traces at the end there are, many requests have been made to the endpoint. And the other thing that you can use it for as well, we won't use it here, but you could also use it for understanding the duration, the total duration of those requests, encompassing all the different operations that are needed across the microservices to deliver, on each individual request. And so by checking on parent ID null, we're just, okay, we just want the top level. We just want to count how many times there's been, how many traces there are stored in the system at the end of the day. And so we get, and this is what we get. We plot that over time, and we get, the request per second. That is, fairly simple example. Let's look at another one, another example that is more interesting. That is something that we can do, because the previous one, you could probably do it with metrics. This one is a lot more complicated typically to do with metrics, which is, if you look at this table, we're showing error rate, but we're showing error rate per service and also per operation, per individual operation. And some of those operations are happening, are inter-service operations, is things that happen just within a service. Some of those operations is a call from one service to another. And by looking at this, we can quickly see that, okay, this one, the extra process upper operation in the upper service is the one that has the highest error rate. So very quickly we see, okay, there are a bunch of errors in the system, but this is probably the service, I should go check in first if I wanna reduce the number of errors. Here, this is the same thing, but plotted over time. And so if we look at this query very quickly, we'll see it's again, we're querying the span view. And in this case, what we're doing, you see these conditions here is because there are these variables that we use in this dashboard at the top. So we use that so you can sell. If you want to filter down what is shown in the dashboard to a specific services and operations, you can. But the only thing interesting here is this. So we do a count on the number of spans, and we're grouping, as you see, by service name and span name. A span name is akin to an operation, and so we're grouping by service name and span name. And here we're counting how many spans have a status code of error, okay? And we're using, this is a subquery, so at the top, we're just computing the ratio, okay? Here we're counting how many spans in total there are, grouped, by its service name and span name, and then we just do we just divide the two and we get the rate. And that's what we're saying here. Okay, let's look at more interesting stuff. Request durations, again. So here we can build, because we have all in this case, we're not downsampling or anything. We have all the data. We can build a 100% accurate histogram of request durations, which is what you see here. And what we realize, just by looking at this, we see, okay, the majority of our requests are delivering less than approximately 2 seconds, but there are some outliers. There are some that they take, even more than 30 seconds. And if we go below here, we see, again, because we have SQL behind the scenes, we can run a query that retrieves the slowest request. So let's take a look at what the query looks like. It's, again, very easy. We do a select, again, on the span view. We're looking, again, at, entire traces, not individual operations, but entire requests that go through the system. And so that's why we're using parent span ID null in here. And we're just ordering by the duration, of those traces. Descendant, limit 10, so we retrieve the top 10. And we're doing some magic, interesting magic here. We're doing this replace, okay? And here, trace ID, we're replacing, basically removing dashes, because we store trace ID as UUIDs, and they come with dashes. But we remove them because then we can do some magic and have this link that when clicked, you can actually, Grafana provides a way to visualize an individual trace, so that you can understand the hierarchy and the sequence of operations and where things may have been wrong. What is slow? In this case, we're looking at the slowest traces. So what is slow? And, very quickly, again, you don't have to copy and paste or anything. You click, it's everything within in Grafana, and you can jump and investigate that specific trace that was slow. And if you look at the detail, you'll see that if you look at the hierarchy that, there are a lot of things that are very fast, microseconds or milliseconds. There are some of them are long, are taking a long time. And if you look more specifically, you'll realize that always what takes time is this digit, random digit call. It's always the random digit call that is, the slowest thing in the hierarchy. Again, here, random digit call. So very quickly, you've identified that probably there is a problem, at least in this trace. And if we look at other traces, there's probably a common problem there. Random digit is slow. Again, very quickly, you can go identify where the problem is, in which operation, in which service, and you can go and go improve, look at the code and improve it. Okay, let's go back to our other dashboard. And now let's look at things even more interesting. And that is what gets really interesting. This is a service. This is showing a service map and how the different services are interacting with each other. So with this, what we're seeing is that which service is calling which service. And okay, everything seems normal. Okay, the generator service is calling the digit service, is calling the lowest service, the special service, and the upper service. But very quickly here, we can identify there is something that is something wrong, something that doesn't make sense, which is that the lowest service is calling the digit service. And that number here, because of the way we've constructed the query, is showing how many requests are being made. Okay, this is the time point that I selected. In the last 5 minutes, there were 2,600 requests from the lower service to the digit service, and the generator service more or less about the same. So why is there so much traffic here? Probably there is a problem. Okay, and it's something that we could again go and check and see what's happening. So how does this work? How do we do this? So we're using a new visualization from Grafana that it's currently in beta that is called the node graph. And the node graph expects two things. It expects a query to return that returns the list of nodes, the circles that you see here, and then a query that returns the list of edges. So that is the arrows that you see in here. And so if we look at this query is just retrieving all the different services. Okay, so it does a select on the view, is grouping by service name, and ID and title are things that need to be returned. Okay, the columns that you return need to have these names for the node graph to work. The title is what's shown underneath the circle. And then the second query returns the arrows. And as I said, so the relationships between the services. And this is something that is usually impossible, with the limited query language that other observability backends provide. But because we can leverage the full capabilities of SQL that are provided by Postgres, we can do joins. And in this case, if you look at what we're doing, and maybe actually I'll move to another editor to make this easier. This is the query this is the query that we're doing for the edges. And so if you look at it, we're doing a join. Okay, we're joining the span view with itself. Okay, so we're joining the span view with itself, and we add two additional conditions. These while not strictly needed, we still add trace ID equal. The trace ID are the same in theory. Just with the span ID, it would be enough. But we do this just to make sure that the span ID, there is no collision in case there is collision in the span ID. But the important part is this. So what we look at is that the span ID of the P, the parent span, is the same as the parent span ID of the kid or the child span. So we are basically looking at relationships. And the other thing that we look at is that we want the service name from both to be different, so that we remove inter-service calls. Okay, this is only returning calls in between services. So again, it's something really cool because it's something that would be it's really hard to do with other, maybe in most cases impossible with other observability backends. The other thing here that we do, we do the same thing, but we do this in a table, and we collect some other stats that are interesting. It's the number of calls. And here, very quickly, we can see that the total execution time was, is where most of the time is spent. We see, okay, the generator service calling the lowest service, and the generator service calling the digit service, and the lower service calling the digit service, which are, in minutes, in this 5 minutes here. And so, given that the lower service calls the digit service, most likely the slowdown, we saw it before, is in the digit service. Okay. I don't know. I'm not sure how we're doing on time because we started, a bit late. But I maybe just show one last example that I find really cool, and then I'll be done. Upstream spans.
You're doing good. Sorry, I just popping in and say you're doing a good job. One last example is perfect timing.
Okay, excellent. Thanks, Brian. And so let's pick the digit service, for example. And so if we look at this, so what this is showing, so I've selected the service digit operation / so it's this circle here. What this is showing is all the upstream dependencies. So it's basically retrieving all the traces where the digit service is involved, and is calling, recursively navigating the tree, the sequence of calls, until the digit service, but backwards. Okay, so that we can reconstruct a tree and we can see that, okay, so the digit service is called by the digit method in the lower service, and it's called, by the generator. So that's basically the tree. But we see, we see two paths. So one is from the generator to the digit service, and another one from the generator to the lower service. How is this useful? Imagine that you're in a situation where you see a sudden increase in the number of requests to a specific service, for example, but you don't know what's causing that. And in a microservices environment, this may be really hard to figure out, So with a map like this, you can actually understand, okay, what is calling my service, and how often are they calling the service. So that is actually really really helpful from that regard. And so if we look at the queries behind the scenes, again, the node and edges, and if we look at it very quickly, I have them here. This is what we do. So we do a query, and we use something really interesting, which is our recursive query. Okay, so we run first this query, and the results of this query are injected, in here, into this query. And so if we look at it, what this is doing, this is looking again at is navigating up and looking, at the parent. So it's retrieving, okay, the results that we got from the first query are here in X, and what we look is for where the parent span ID is the span ID of S, which is what we're joining with. And we're returning the parent span in this case, and all these results get injected again in the same query. And it does this again and again and again and again until this query returns no results. Okay, and finally, from all those results that were collected, all the hierarchy of results, this is what we're projecting. So we project an ID, which is the service name and span name. And then a few pieces of metadata that we show in the map. And here the query is very similar, but in that case, we're calculating the edges, so we're projecting some additional information, but it's the same. It's the same join happening here. Okay, and so with that, I'm just gonna encourage. So we've seen that OpenTelemetry PromScale, how you can use OpenTelemetry PromScale and Grafana to get invaluable insights, thanks to the power of full SQL support. And I encourage all of you to download the OpenTelemetry demo today. all the software we've shown is available on GitHub and it's free to use. And if you have questions about PromScale or the demo environment that we've shown today, we're available in the PromScale channel on our Slack community. Thank you so much. And, I really hope to see you soon on our Slack community.
Awesome. Ramon, every time you show those dashboards and I think about what's going on behind the scenes, it just excites me so much. It's so fun as someone who loves SQL, just seeing that work. So your team's done a great job. Thank you for that. We actually have almost gotten back on time here. So even though we dropped, I did just want to ask real quickly. So, as we're adding an open telemetry, people that might already have been doing some of this, and if they want to start to incorporate PromScale in some way, what are some things they might need to think through?
Yeah, so on the open telemetry side, something really interesting is that for the demo, we used manual instrumentation. But something really cool is that open telemetry does provide auto instrumentation. Okay, so you can actually use libraries without changing your code for a number, not for all languages, but for languages like Ruby or Python, Node, Java. You don't have to change your code. You can use those libraries and very quickly get your systems instrumented. And then you can leverage PromScale has native support for open telemetry, so you can send all those traces that get collected to PromScale. It's a good way to get started, and then from there you can start looking. Okay, do I have more needs for instrumentation? And you can add manual instrumentation on top of the auto instrumentation. It helps you get started much more quickly than if you had to do everything manually.
Great. Very cool. Well, thank you so much. Excited to see what else is coming from your team. I know we'll be talking more about observability in the next month or two. As we said, this is, streaming today is kind of a culmination of a week of releases, or what we call always be launching around Timescale Cloud, our hosted service. And we will have one of those weeks coming up in the near future for observability updates, improvements, and features soon too. So excited for that.
Yeah, really looking forward to that.
Great, Ramon. Thanks so much. Have a great day.
Okay, thanks.
Bye. So Miranda, here we are. We're at the end of the day.
Here we are. And
so little known fact in the world. Miranda and I live approximately how far from one another?
Like a mile and a half.
Yeah, not very far.
Quite close, which is really awesome and very convenient most of the time, except that on one side, except for this moment, because one side with facing towards this window, it's like a beautiful, awesome, like summer day, what it looks like, spring day. And then behind me on the other side of the mountain is literally the most ominous cloud I have seen in a long time.
Indeed. Yeah, like perfect timing. We joked about Scott. I'm actually I'm going to look that direction real quick. And I agree. It's blacker than black. So Miranda and I are doing this last talk, and there's a relatively decent chance we might lose power. So we're going to give it a go. If it doesn't work, so between weather, restream, a whole bunch of stuff, it's just after us at the end of the day here.
And it was so smooth. It was so smooth in the beginning.
The first 4 hours were complete. And I'm thankful because we had so many good speakers.
We did.
Many good sessions. And I'm thankful that all of that went without a hitch. And if anything's going to, have a problem, then it might as well be the stuff that we're presenting. Because we can do this anytime, but just what a great time.
Yeah.
So if this doesn't go well, if the power goes out and Miranda and I disappear, our community manager, Lorraine, will take the reins and close the day up for us. And we will record this session, at a different time and post it as part of Community Day. Honestly, because it's just fun. Miranda and I love quirky little, statistical things. She's much better at statistics than I am, but I love talking about it with her. And so I think we're going to go ahead and get started. Attila, you can share Miranda's screen. And Miranda is actually just doing the slides for me. I see I see 𝗙𝗶𝗽𝗱 right now. Do you have the slides?
I'm also muted. I'm also muted. I apologize. I thought you were going to do the slides. So
I'm happy to. I can do
Do you
stuff
have
from here.
them up? I thought I was
I
just
have it
doing
up
the
right now.
code.
No,
Clearly,
it's all good.
we're wrapping up this day strong.
It's been a long day,
Tell
guys.
you
It's been
what.
good. All right, let me get my screen sharing here in just a second.
And I really appreciate is it 𝗔𝗯ance? I'm really sorry if I mispronounced your name. But yes, I appreciate that you feel this energy with us. Thank you. Thank you for being understanding. It's awesome.
Okay, so I am using Chrome, which I don't normally use, and I can't share my screen. So can I send you a link and you can get in there real quick?
Yeah.
Since
Yep.
you are working. My
Mhm.
apologies.
Oh, just Andrew. Okay. Yeah. Cool. Thanks, Andrew.
All right, there we go. So that way Miranda can just share this from her screen and we'll get it rolling. So here's the deal. Wordle has been one of those little things that seems so innocuous, right? Like, whatever, it's a one puzzle a day. And when it first started happening, I didn't know, I would see these tweets. I didn't understand what those little boxes were that were showing up in my timeline feeds and everywhere else. It just kind of confused me. And so we wanted to, I started seeing them, started playing the game. My family enjoyed the game. And I wanted to start to figure out, can I tell anything from the result tweets? I'm not looking, there have been people that have written all kinds of stuff in every language about how to solve a Wordle puzzle, right? Like they know there's 12,000 5-letter words and they know this and that. I wasn't looking to do any of that. I was just like, what could I tell over a period of time about different puzzles, maybe statistically how likely people were to get a result within 2 or 3 or 4 guesses, depending on how good their first guess was. It just interested me. I'm like, it's just these green and yellow boxes. What can I do? And so that's what we're going to talk about today. It follows on nicely with Jim's talk. So Jim works for Twitter. And for this, I had never used the newest API of Twitter. So we have been streaming some Twitter results into a database. And we want to talk to you about how you can take something as simple as some emojis and turning that into usable data that you can do queries with in Postgres. And I just think that's kind of cool. So go ahead and advance the slide. Here's the basic agenda.
Oh, will you let me change the slide? There we go. I'll just have to do it manually.
So we're going to talk about what the results data looks like, how we can actually take that. So mining the API really briefly, and then extracting that data. How can we turn those little blocks of emojis into something we can do? And then Miranda has a bunch of really fun little queries to look at, like actually answering some of those questions. It's really cool. So let's go ahead, advance the slide. So Wordle data. So we all know what Wordle data looks like. The next slide. Right. This is yesterday's. I hope I'm not, what's yesterday's? You can't get back to, right? So
just ruined it. No, I'm just kidding.
I did. I ruined it. I had solved it before I did this in 4, not in 3. And so
I was going to say, this is kind of too good, Ryan. Are you sure?
I know it's too good.
Kidding. I'm kidding with you.
No, I almost had it. I almost had it in 3. I actually had stove and then I'm like, that's too easy. So I turned it to stoke. I was kind of upset. Anyway, so we take this and then at the end of the game, you can go ahead and put your emoji up in social media somewhere. You can just share it. And this is all we get. Now, there are at least 4 combinations for the exact same thing because there's a high contrast colorblind mode and there's a normal mode. So we had to be able to count for all of this to find the data. And so I had to, learn a little bit about the Twitter API, some of the new improvements they've made so that I could query this data and stream it into a database. So let's go ahead and see what we did with that. What could we get from this grid? I wanted to know. Inquiring minds want to know. So we connected to the Twitter API, and I had to learn a little bit about it. Now, Jim gave you some great links in a previous talk. If you missed that talk, please find it in our YouTube feed. If you're watching this talk afterwards, it was by 𝗔𝗵𝗽𝗀𝗀𝗀. It was about using Twitter for weather emergencies, flooding and so forth, and warning systems. And so with the new version 2 of the API, they've improved the way that you can kind of query this in their own language. They're like querying natural process language. So I looked at the tweets, I looked at the result thing, and I had to narrow down the scope because as with anything, that is popular and good, what happens? There's 100 different knockoffs with all kinds of combinations that might look like a Wordle puzzle, but it's not. And I knew there was no way to guarantee, right? This is just it's a tweet. Anyone could compose a tweet. There's no guarantee this is from Wordle, but we had to do the best we could. So these are some of my parameters I wanted to know going in. I just want to look at the English versions, ones that were posted in an English language. Original tweets only. A lot of people like and retweet and reply to them. I didn't want to, get those for one reason. And that is just there's a limitation in the number of tweets you can consume every month currently in that API. And so I just want to eliminate all possibilities to not use up that quota too quickly. Maybe limit it to countries. There's a lot of countries have, different variations. And so if I could, I was going to try and see if I could figure out geotagging. Recent games only. So, people, again, compose tweets that aren't actually for today's. We were getting tweets originally like game 1, game 8,000, so wasn't worth it.
I think the most impressive was one person in the before we put on this parameter that one person tweeted, it was like 10 or 15 games in one day. And I was like, the dedication, I love it.
Which means they're going in and changing their clock, right? Like finish the game, go change the clock, finish the game. And then last but not least, I realized halfway through, and partly because of my son uses he's colorblind. And so, hi Bart, how you doing, buddy?
Yeah, sorry. I was
I know. I saw
excited that Bart was there.
So I realized I wasn't originally taking into consideration the high contrast colorblind mode either. So I wanted to do that to kind of get the full bandwidth gamut of responses. And honestly, I actually have a small group of friends that I do a Wordle puzzle with, and we share results every day through an app. And one of my friends is colorblind, was tweeting his, and I wanted to capture them just so I'd have them. That was the other reason I did that. All right, so there's our parameters. And so what that ends up looking like with the Twitter API, if you go to the next slide, is this kind of query. And so there's probably other things I could have done. I tested a bunch of things, and honestly, the easiest way to do this was by going to Twitter because I wasn't using up my API limit, testing various search parameters. You can actually do some of this right through the Twitter search API in Twitter. And so this is what we came up with. It has to have the word Wordle. It has to have combinations of the red or orange and blue box, or combinations of the blue and green. It turns out that I could have added the white and black as well. But through the Python API, I talk about this later, I was just having problems getting it to actually save. Those two emojis start or end, I forget what it is, at a different part of the UTF character set. And something about the Python, it did not like them. I could get them, but I couldn't save it to the search. So I gave up. I said, we're just going to do this. And then isn't retweet, is not a reply, is not a quote. And I actually added the -es. There's a lot of English postings. So language is English, but they're from the Spanish version, apparently. And so I was just getting lots of those. So I cut that out as well. So using that search, we are able to get a tweet that looks like this. This is the data that we would get. It's a JSON packet, right? It's pretty straightforward. Now, through the API, which we're not going to get into, you can decide which parameters you get back in the JSON response. For our needs, I mostly wanted to know user, time of day, the tweet text, and then I wanted to know the location, whether they were verified, in case in the future we wanted to do something with that. Now, it turns out the location is not geolocation. Anyone can put whatever they want there. So we had lots of people from, Disneyland and the North Pole, things like that. So it realized it probably wasn't.
How do you know that they're not from Disneyland, Ryan?
That is true. They could be living there.
They could be living there.
Yeah, doing Wordle every day. This is where I go to do my Wordle puzzle.
Hey, maybe they work there. I don't know.
Who knows? Yeah. All right. So we have the data, and now we have to figure out how to do something with this. So this is the packet that my streaming Python script is getting, and I had to figure something out. How do we store this? Well, what I did realize along the way, just want to bring up a couple things, again, as a kind of a novice user of the new Twitter API, the V2 API. For some reason, it wasn't worth me spending, if you want to go back one slide, it wasn't worth me spending a lot of time in this, but something about the Python SDK that they are providing, or maybe it's something I was doing, those two emojis, I just couldn't get the Twitter streaming API. So basically you set that search string. When you start your connection, you say, here's my search string, and then you subscribe to that stream. I could not, I tried after 45 minutes, I'm like, I'm done. It's not worth this. So I just took those out of my search for now. If someone posted a Wordle result that had literally no yellows or greens, that's a really, really bad day. And I don't know how you get that. So I was pretty confident I would get at least one with a green or a yellow or a orange or red, blue. Streaming was inconsistent. So again, this is not my primary job in life. Some days, in fact, the stream's been going for about 18 hours now, the streaming API request. But then some days it would stop 5, 6, 7 times in a day. And I'm sure there's a reason. I just haven't had time to reach out and figure out why that is. Something to know. And then currently the limits are either, I think it's 500,000 or 2 million tweets per month. On the V2 API, they don't have a way to buy more. So with this current, we get about 130 to 160 tweets, 1,000 tweets a day. That means we could probably get 10 to 12 days of data per month. So today's data set has about 5. Some of those are inconsistent because the script stopped now and again. And like I said, there's no way to distinguish real versus fake because it is what it is, right? All right, so we had that JSON packet, and then we had to figure out how to store it. So they're really, the main thing here was, do I want to do processing in Python beforehand, or do I just want to save the JSON data and go ahead and figure out how to do it all in SQL? And, after I spent a little bit of time, it just seemed more efficient to go ahead and create a schema like this. We probably could have done more. That stored the basic information first. I didn't pull everything apart. The JSON, the Twitter post was left untouched. I did all of that work you'll see in a minute in SQL, partially because I really wanted to see how effective or efficient I could get at transforming all of this, something I wouldn't normally do. And so go ahead and hit the down arrow. You'll get a little box. The one thing we did do is I still saved the whole JSON text that we got from the API in case later in life, later we're like, oh, I wish we would have X. Well, we still have the JSON response and we could parse it apart because Postgres is great at doing JSON querying, right? So that's what we stored the data into. So this table currently in our system has, I think, about 500,000 or 600,000 rows, something like that. So now we have the data and we need to now transform it. I still can't do much with this. I know, who tweeted it. I know whether they're verified. I know the time of day, but I don't know what they're, and I know that they got the puzzle in 4 guesses. But I don't know anything else because it's all trapped inside of that tweet and I want to extract it some. And so we take, I did not. So thank you for the question. That was a sample just as the overall schema. I'm not getting into the details of, what indexes and so forth, mostly just because we have such a short time to talk about this. Miranda and I will be working on a post that digs into this a little bit deeper. Hopefully in the next month or so. We both are talking about how much we enjoyed this. And so we'll try and give you a little bit more info, just kind of how we approach some of that stuff. So great question. I'm just not showing you all the details here. And so now I have that data and we're going to go ahead and extract it, right? So this is where I think so many people, you can go to the next slide. So many people forget, or maybe they just don't know, they come from a different technology and they do end up doing so much work inside of like a Python script. And Miranda, you and I have talked about this a ton. Where in data science, even there's so much power in something like Python, but you end up doing so much of this stuff in a script that really could be parsed down into the database if it has the ability to do it. Now everyone gets access to it. You don't have to pass scripts around that are doing all this complex array logic and pulling things apart and transforming text. Could we do all that in the database? And so that's what I wanted to see. And so now I need to take those boxes, right? There's, in theory, a total of 30 boxes, little emojis that could mean something to us. So every row is a guess, and every position in that row is a letter. And you either get the letter right, you don't get the letter at all, or you got a letter, but it's just in the wrong position. It's somewhere else in the word for the day. So we could go about storing the results in one of at least 2 ways. We typically talk about this in time series world. whether you do a wide table for your time series data, which implies that for every row, it's a time-stamped event, and all of the unique pieces of information you want to know about that timestamp are in that row. So you literally spread it all out. So in something like this, I might have 30 columns, one that represents every possible letter for a full puzzle. The original matrix, you're really spreading this whole thing out, which in a situation like this didn't make a lot of sense. If those were unique measurements, that makes a little bit more sense. It's a little less easy to use, or probably a lot less easy to use, to query things by 30 different columns when you're trying to find this kind of data. So what we did instead was to go to, in the next slide, the what we would call kind of a narrow result. So we take one tweet, which is one row in the other table, and we break it apart into however many guesses there were in that tweet. So the guess table that kind of pulls all this apart has one row for every guess of that user's tweet for that day's puzzle. So if they got it in 3 guesses, they only have 3 rows in this table. If they got it in 6, they have 6 for that day for that puzzle. Now, the nice thing here is, you can do a lot of indexing on specific columns like guess number. When you're querying for position, you're not having to think about, well, it's position, 1 and position 6 and position, for each guess and so forth. So that just makes it a little bit easier to work through from a query perspective. And then as we were going about it, the other thing that we thought, just from a data science perspective, when you're thinking about querying data like this, yes, we could have simply done a lot of work so that all of our queries only looked at the 5 columns that represent that day's, each letter of that guess. But really, if we're already processing the data, why not just pull it apart and go ahead and count up how many correct and incorrect values for that guess, not position, but how many, so we could slice and dice a little bit easier down the road. And so we take all that. This is the sample query we came up with. We're going to breeze through this. Again, we will probably have a, someone is holding a hope. Yes, we will do hopefully the thunderstorm isn't coming here for the last couple of minutes. So if you go to the next slide, there's a lot that Postgres can do. And I'm going to really quickly keep going. How do we turn this into meaningful data? This is one sample query. Now we will at some point in the future parse this apart in a little bit more detail through a blog post or something. The basics are this: Postgres is really great at arrays, in doing regex, a lot of things you're normally used to, but now you can do this in the database. And so the long and short is, this is a script I made. It's I say script, it's really just a single query that uses some things not necessarily known about in Postgres, things like locked for update. And if you want to hit down a couple of times, I think I highlight a couple of these. Basically, we're taking 100 rows at a time. This is just as the data is coming in. This query is also running. It's taking 100 rows of data just over and over again from the table. It takes that data, says, hey, does the tweet have at least one row of 5 emojis that match any of these together, right? And so if it does, it splits it out as one result row. And then we take each of those result rows, we clean it up into effectively numbers. So rather than red, yellow, green, because we have 2 different variations, we just said, hey, 2 means they got the letter in the right spot. 1 means it is the right letter for the word, but the wrong position. And 0 means it's just the wrong letter. That letter doesn't exist today. So that's what the clean guesses means. And then finally, we take that guess and we actually do the count of how many correct, incorrect, and partials we have. And we finish it up by inserting it into that table. And so you can skip through the next couple slides. I just really quickly talk about this. I break these out. So this is saying, hey, are there 5 per row? It does the ordinality, which is really necessary because it gives us the row number. What the guesses are, changes them into numbers to make it easier to process because there's those variations, black and white and yellow and I think orange, and then blue and green. All those things mean something different. So, and then finally, we actually take that cleaned up guess, we split it apart into the individual characters to save it into that guess row, and we have our counts. And so that gets us that table of information. So from, I didn't do the counts for the last couple hours, but I think that's the end of the slides. So Yeah, so that means this gets turned into something else. We're going to look at some queries. Oh, sorry. So this is the, yeah, I did forget I actually had this. This is
I
what
was going
that
to
would
say, we're
mean.
not
So
close to the end of the
not quite
slides.
there. Well, there's some other stuff that I just copied at the end. That just means every guess has a numerical value. So every, how many guesses, this is guess number 1 in this case for game 279. Letter 5 was correct. It was the right letter in the right place. And letter 3 was a correct letter, but in the wrong place. And we can see that we have 3 letters yet to guess, 1 that we need to shift around and so forth. So that is what the result looks like. And now we can go ahead and run queries on it. All through SQL, just taking that text, those emojis, doing a little bit of SQL on it, and splitting it out. So I think you now have the queries itself to show.
Yes, I'm going to pull up 𝗙𝗵𝗽, which we now have. If you're not familiar with 𝗙𝗵𝗽, it is a common GUI tool that we use to kind of do Postgres queries, essentially, and timescale and stuff. So Ryan kind of gave you a quick overview of the data and how we are storing it and all that good stuff. So now we can start to ask some of the questions that actually, have us analyzing the data, right? Because that's really the whole goal of collecting data, is to analyze it. So we'll just go through a few queries here. And don't worry, we will, like Ryan said, we're going to do probably a blog post on this later, because we have lots of fun queries that we want to cover, but just don't have time for. So kind of one of our initial thoughts is how many Twitter users do we have tweets from in total right now with what we have in the data in the database right now? And so I just do a count on unique author ID, and then also do a count on unique tweet ID. So that should give us the number of people that we're collecting tweets from, and how many tweets that they actually made. And so as you can see, we have 228,000 distinct users that we're collecting tweets from, with a total of 510,000 tweets that they, made total. So how about some more interesting things? And so one thing that Ryan kind of hit on earlier is that we can't guarantee a lot of that we're getting super clean data here. So of course, we want to check, are there instances where we're getting tweets that probably shouldn't be counted, when we're trying to actually do analytical queries, like looking at, the average guess time for a certain game. We don't really want cases where we might have 10 or 13 different guess lines, from a tweet that somehow got into the database system. And as you can see, so if I run this portion of this select statement, this is grabbing the unique tweet IDs and then the count of guesses for that unique tweet. And as you can see,
Someone
and this is
really
only
went for it with 24.
Yeah. So this is all. So these are only counting and showing guesses where they have more than 6 guesses, because for me, I'm thinking, if we want to try and filter out the bad tweets, and in Wordle, traditionally you only have 6 guesses. So if someone is guessing more than 6 times, then probably something is wrong with that tweet, or we're just collecting too much information. So that's why I put that having the count of the guess greater than 6, just so that we can figure out what tweet IDs are kind of bad or just dirty, not ones that we want to have part of analysis. Yeah. And someone, so this tweet ID, there were 24 counts. And in fact, we can look at exactly, just because I think it's fun to double check what happened that we had 24 guesses. Is this accurate? What's going on here? Because I also, whenever I'm doing any kind of analysis, I want to dig into what's happening, so I can kind of understand. And so if we look at the tweet, here so this is the information table, and this column has the tweet information. And so if the zoomed in version, you can kind of get okay. So as you can see, it's somehow I don't know if it's that they copied in like a bunch of Wordles in one tweet, or we don't really know what's happening there, but it is accurate that they had 26 guesses. And of course, we don't want to include those for our analytics functions. So, and if we run the CTE of kind of pulling these filtered tweets, we can see that there are 947 tweets in our database that are counting more than 6 guesses. So that's 946 tweets that we can kind of like, okay, filter out, throw those out, because those are gonna like cause issues with any kind of analysis. So now that we have kind of like those filtered tweets, I'll actually skip down to the filtered tweets. So this portion right here is basically just grabbing the tweet IDs for only the clean tweets. So it's just, I'm putting that parameter that the count has to be less than or equal than 6. And then with that parameter or that constraint, all the tweet IDs theoretically should be, there's a higher likelihood that they're okay to include in analysis. And so that's just kind of like a quick filter to just give us, again, like you would, for official analysis, you would want to do way more cleaning, like way more.
We only got a few minutes here.
way more cleaning, yes. So, that's just what the CTE part of this is. And then we can select the average guess amount, filtering for these 2 games. So I just want to look at 2 games in particular. So that's like 2 days of data essentially. And then I just join with the tweets. And so we can, get an idea of like, oh, for game 279, people had a better chance of getting it on average than earlier, rather than 282. So that's like, cool information to keep in mind. And then the last query that
I'm not going to lie, 282, I got it. I didn't get it. There were too many choices and I was annoyed.
Yeah.
That other people suffered too.
Yeah. So that's actually this last query that we're going to look at is looking at kind of exactly that to see, I want to look at game 282. What happened? So this query that I'm going to run, so this first part in the CTE, if I run that, this is giving me the total. So this column tells me, essentially I used our time bucket function from the Timescale DB time bucket function to bucket all of the tweets per hour. So I'm counting how many tweets are being like collected per hour. And then I'm actually giving the results for when they won. So like per hour, the counts of tweets that got the correct word per line. So for example, if we look at this row 3, there were 85 total tweets. Do you mind moving us, Attila, to the side?
Move me out of the way for a minute.
Yeah.
There you go.
It's a little bit smaller, which I apologize, but at least that way you can see the query. So a total of 85 tweets were made in this time bucket hour. 20 people took 6 guesses to win the game. 18 people took 5 guesses to win the game. 28 took 4, 15 took 3, and so on and so forth. So that's I just broke up like, how many tweets, like what the kind of like spread was per hour. And of course, like for me, since there's such a varied amount of people putting in tweets per hourly bucket, it's hard to see like what percentage did people, like how many people generally took 6 guesses versus 5 guesses versus 4. And so that's the second part of this query, is just taking the percentage of each guess, like given the total.
Okay.
So if I run this whole query, now I'm actually just taking it, I'm looking at the percentage based on the total for that time bucket. So if I look at this row 10, 24% of people that tweeted at
During
this
that hour.
time, at that hour, they took 6 guesses. And then 25% took 5 guesses, 27% took 4 guesses, 17% took 3. And as you can see, it actually was pretty consistent over the day. Like
Was.
it's depending on the hour, people generally got about the same spread for how long it took them to get the Wordle. So that's kind of an interesting, start to analysis that you could do. I think that's pretty much all we have time for right now. But
You just do the one really quickly. Do you have that last one? Just do one of them, the L2 guess. I think you have down below.
L2 guess.
I think it's that one right there.
Yes,
So
yes.
just
Okay.
an example of, this is one of the questions I've always had, like, hey, if someone gets it, has so many letters in guess number X, 1 or 2, how likely are they to get it before 4 guesses or something?
I'll run
So I
both
think
of
you
them.
did this here. Okay.
Yeah. So if you get for the game 282, if you get,
Which I did not get.
If you get at least 2 letters correct, so not partially correct, they're correct in their right spots. Generally 25% of people could get it in 3, 27 in 4, 23 in 5, and 23 in 6 guesses. Versus
really interesting.
If you don't have 2 letters correct for that game, 13% got it in 3. And then it's kind of like a higher. So I mean, to me, this definitely says you could probably analyze this further. And it would indicate to me like, oh, I probably, there could be something here that if you get, 2 correct within the first 2 lines, you're more likely to get the answer sooner, which makes sense, but it's cool to have, like some weight to that and validate, like looking at this from a more statistical standpoint. So
that's so cool. Very neat.
Yeah.
Yeah, there's so much
super
here.
fun data here.
I mean, I loved, we were talking the other night, about this data, and we're like, oh, I don't know, can we show much? And I think that all of a sudden, 45 minutes later, we're like, man, what else could we look at? It's something so simple. And that's the power of data. And honestly, for us, we say this is the power of time series data. It's the power of being able to do it with SQL is so much fun.
It is. And it makes it so easy. Like, probably none of these queries were optimized because we kind of created them last minute.
As we're talking. I know, we were talking about it. What about this?
What about this? What about this? But that's kind of the beauty of SQL, is that you can explore, and it's like so easy to explore data and so easy to kind of like play around and clean it up and figure it out. Like this was, just scratching the surface of what we could do with this data set, and hopefully what we will do with this data set, because I think we're going to try and do a blog post or multiple.
Or multiple, who knows?
Yeah, who knows?
All right, that was awesome. Yeah. Thank you. Well, the time has come. I looked out my window, I think
it might be passing us.
Past. I think it moved past.
It's a miracle.
Sometimes the mountain bumps it out of the way.
A community day miracle.
I know it is. I think we're about done. You have a little bit to, we've been waiting all afternoon, all day to get to the end so we could do our trivia. And again, if you're watching now, this is going to be with a tool called Kahoot. So Miranda's going to share it with you. You can go and take part in the trivia, and then we'll get in contact with you to give you some swag packs. Thank you to everyone who's taken part, both the speakers throughout the day. We literally couldn't have done this without you. And the talks were they were top notch. And I'm just so thrilled to have been able to connect with each of them. Miranda, thanks for all of your help, just getting this whole thing rolling. And there's so many people behind the scenes that have worked really hard on making this day possible. So congratulations and thank you to all of you. And we're just so excited to have you be a part of this community. And again, we've said this a few times throughout the day. If you If you're not already, please consider coming and joining our community Slack. We have a new forum that you can post all kinds of questions to, and we'll do our best. We continue to see more interaction through the community, which is so much fun. And look for more things from us on YouTube and elsewhere. Lots of good content coming, already in process. And do we do this before or after the trivia? Announcing the next.
Oh,
do you do it now?
well, I guess I don't know. That's a good question.
Okay, tell you what. It's a good question.
We'll do it after, maybe.
Okay, sounds good. We'll do it after. I like that.
Okay.
All right, so let's move on to
decision.
the trivia. We did. Let's move on to the trivia, and we'll be back at the very end.
Okay, so I shared my screen. All right, everyone. It's trivia time. I'm hoping that this doesn't show the answers when I press start. So this is my first time actually running a Kahoot game. So we'll see how this goes. So yeah, if you are new to Kahoot, I've played them before though, so I know that part. So you want to join at www.kahoot.it or with the Kahoot app. And then you just want to have this pin. I guess I can copy to share. I'll have this. I guess that's the link. Copy to share the game link. So we're just waiting for players. And remember, you get some free swag if you play the game. Oh, and there's 3 people that get the opportunity to win free swag. So, if let's see who's going to join here. Oh, there's 4. Okay, so now there's competition. Yeah. All right. I'm going to give maybe one more minute to join in. If you want that chance for the free Timescale swag, you want to join now. Don't miss your chance. Don't miss it.
When I wish I could beatbox, but I can't. Didn't you say that? Does your husband beatbox?
I'm terrible at it. Cam actually does beatbox, which is hilarious.
Which is really awesome.
Yeah. Oh my gosh, so funny. Okay. Wow, we're getting some people up in here. This is great. 11, 12 people. Okay, we're gonna start it. Anyone
5,
else coming?
4,
3,
2, 1.5. No.
All right.
1. Go.
Oh wait. I just heard that we got it tweeted again, so we're just gonna give it another just a little bit of time.
Oh, okay. We'll wait.
While we're waiting, I don't know. Does anyone have something fun that they're gonna do this weekend? Something super cool? I think I'm gonna
coach my first Little League game.
That's awesome. That's exciting.
I've never coached in my life, and I'm gonna help coach a Little League game. So this could be fun for everybody.
Yeah, that's super cool. I commend you for that. I don't think I could coaching, especially for I don't know. It seems like a lot of pressure. That's cool though.
I hope it's not.
I respect it. I respect you taking time to do that. I think I'm cleaning coal out of my basement this weekend because apparently I live in the 1300s.
Mathis is gonna go camping in the desert. Hey,
Whoa!
it's cold at night, I'm told.
That's cool.
Dress warmly.
That is super cool. Camping in the desert? Man, that's awesome.
That's awesome. Which desert?
That's a question.
Yeah.
Which desert indeed?
Well, we just actually lost link to our chat feed here. So
yeah. So
all right,
we
let's go ahead.
No. Gonna go ahead and start.
I think we do.
Okay. Yeah. Y'all ready for this?
Kahoot.
Community Day trivia. Okay. Quiz time. Okay, what was the original logo for Timescale? So this was the
click the color.
original. and you click the color for your guess. So you should have options for which answer. So go ahead and you only have 5 seconds left.
It's 3 options. Which one is
3
it?
options. Which one? Okay. Okay. It was in fact the mountain shape. It was that was the original, one of the original logos. But fun fact is that the other 2 logos were options that were being considered. So that's cool.
I forgot about that.
All right. Next question. Are you ready? Are you ready? Oh, okay. First it has to tell us who's at the top. Okay. Second question. What is a group of tigers called? An ambush of tigers, a striping of tigers, an ensemble of tigers. What is a group of
I just
tigers
know I
called?
don't want to be ambushed by tigers. That's all I know.
Yeah, that's
That is
for
not a
sure.
hint. It's just something that I don't want.
All right. And it actually is an ambush of tigers.
Oh man, I didn't know that.
Now you know.
There you go.
Yeah, good job, everyone. Let's see the results. Oh, we got some moving and shifting. Let's see what comes next. Okay, next question. What was the name of the original Postgres query language? Wow, language. PostgreSQL, SQL, PostgreSQL, PostgreSQL. What was the original Postgres query language? The original.
Actually, I don't know that I know.
It is, in fact, PostgreSQL. I had to research that one.
Do you know the previous database of Postgres? A lot of people love to talk this through. I missed out. Darn it.
This database, were you going to say something?
Yeah, sorry. So Postgres comes out of, I thought that's where you were going. I was like, wait, now I'm confused what this question is. So it was carried onward from an application, a project called Ingress.
Yes.
And so this is the post, this is after Ingress. So Postgres is.
And then it turned into Postgres with what was just an S into SQL, which is now, and that's whenever they added SQL as a query language to, like, instead of the PostgreSQL as the query language.
The more you know.
Postgres history. Yep. Okay. Next question. Which option is an official measurement of time? Gibbs time, Planck time, hammer time, and quarter night. This is an official.
Not careful. I'm gonna do my hammer time dance.
Measurement of time. I wish that you would do that right now. That would be amazing. Come on, Ryan. Yes, I love that people chose hammer time. Yes.
That's so
I was
great.
very proud of myself whenever I put that in as an option. So thank you for humoring me, everyone else. Oh, this is awesome. This is great. Wow, there's like a lot of shifting going on. Okay, last question of the day. Nintendo began as a company that sold which products? A beam gun, a home console, like home game consoles, playing cards, or shogi? I hope I'm pronouncing that right. I know that
what is show? I don't even know what that is. What is that?
It's like a tile game. It's like it's a traditional Japanese game. And it is playing cards. You guys knew your Nintendo history. I was hoping I tripped some of you up. So all right. So who are the winners? In third place, we have RB. Second place, we have Hi Friends. And first place, boom, Martinovo. Wonderful job, everyone. I make sure RB, Hi Friends, and Martinovo.
I love how they're dancing. Like that. I could watch that all day long.
Oh, it stopped. Okay. They were like, we're not going to have you watch us all day long. So for those of you who won, so RB, Hi Friends, and Martinovo, please email the Timescale events team or hit us up on Slack. We can't see the chat anymore. So if someone on the Timescale team could verify that, or DM us on Twitter, that also works. You can DM us on Twitter. Did we get information about the email that they could email? I just need a yes or no, because we can't see the chat because it's broke. Yes. Okay. Sweet. All right. And now that takes us to the arguably most exciting news of today. Maybe. I think it's really exciting. We're doing another community day. Woo!
Boom!
Mark your calendars, folks, because we are coming at you once again, October 5th, 2022. We're going to throw down, learn about time series data.
It's awesome. So here's it is. So here's the other cool thing. This is the second one we've done. And the first one, it was kind of invite only because we just wanted to test the waters. It's the first virtual event we've done as a team. You know, the marketing team and the dev team has been growing here. And so for this one, we had a call for proposals, had a lot of great submissions. That was awesome. But again, a little bit compressed at the beginning of the year. So we're going to give this one, now that we're getting in a flow and the weather storms aren't knocking us offline, we're going to go ahead and give you a little bit more time. So I believe in May at some point, and that's the one thing, I have too many windows open, and I thought I pinned that, but now I'm not seeing it, and I'm really sorry about that. We are going to open up a call for proposals. So just watch our Twitter account is honestly the easiest way. And then we'll have a period of time for that window to be open. We would love to continue to have more people join. You saw the variety today. This is not a Timescale only event. That's not the intent. We are so thrilled about the ways that people are using data like this. I've learned a ton today, things that I never even considered, right? And it's just so exciting. Yeah, it's so exciting to see all that. So please think about taking part. Reach out to us on all those channels we've talked about. Get to know who we are. We'd love to get to know you and help you as well. That's super exciting. I love that we know this already, and we're going for it.
I'm so pumped. More learning. Yes.
All right.
Can never get enough of learning. Yeah. Thank you all so much again for coming to this community day, giving us your time. Yeah, this was just so much fun, as always, as it has been 2 times now.
I was going to say, what's really impressive to me, we had a pretty major tech outage, like the Restream platform crashed on us, out of our control. Then the weather stuff happening, that we couldn't get people in. We're only 10 minutes late. This was an awesome day. This has just worked out so well. Great work, everybody.
And it was made most awesome because of our incredible speakers and for all you awesome listeners who took time out of your days to come join us. So,
absolutely.
Yep.
Thanks, everyone. Have a great rest of your week and a good weekend.